Select the major product of the following reaction sequence. If we take a look at what we have, we see that we are starting with bromobenzene. So we've got an aryl halide here as a general class of compounds, and we are in the very first step reacting that with magnesium metal, and we have diethyl ether solvent. So let's recognize what that actually looks like. So that is diethyl ether, and that's our solvent. It's often abbreviated also just ETO. Okay, and so what should happen here? If we've got magnesium metal in an ether solvent and we add in some sort of aryl halide or even an alkyl halide or a vinyl halide, then what's going to happen is the magnesium is going to insert in between the carbon-halogen bond. So that's what's taking place in this first step. So I'm just going to rewrite the reaction conditions: magnesium metal, diethyl ether. And so that magnesium is going to insert in between the carbon-bromine bond. So I'm now going to draw this as MgBr. And so hopefully we recognize this sort of reagent as something that we have called a Grignard reagent. And we should recall that Grignard reagents are very strong bases and also strong nucleophiles. And in the case of this reaction, if we take a look down to what we're reacting with in the second step, we've got a ketone, and the carbonyl carbon of the ketone is an electrophile. So we're looking at this Grignard reagent reacting as a strong nucleophile. So what I'm going to do is I'm going to draw another structure for this Grignard reagent. I've got it drawn here as a covalent bond, but that's a very, very polar covalent bond. And so we can actually look at that as though it was an ionic bond. And I'm going to draw it that way because I think it might help us to be able to see what's going on in this reaction better. So if I draw it this way, like it's ionic, now I can really see that it's that carbon atom that's nucleophilic. And so when I add in the second step and I add in this ketone, hopefully this will allow me to better see where I am forming a new bond. So we've got the nucleophilic carbon atom of the Grignard reagent and an electrophilic carbonyl carbon. So let's have those react. So that nucleophile should attack the carbonyl carbon. When you do that, the weakest bond is going to break, and that is the pi bond. So break the pi bond. And as we've seen in past reactions of carbonyl compounds, our intermediate is going to be tetrahedral, where we've broken that pi bond. So we should have a new bond to that carbonyl carbon from the benzene ring. That carbonyl carbon has a bond to oxygen, which now has an extra lone pair of electrons. And it's also got two alkyl groups. We've got a methyl group on one side and an ethyl group on the other. So I'll put the methyl group here and the ethyl group here. And now in past reactions of carbonyl compounds, sometimes we've seen that these electrons will come back down and push off a leaving group. And for something to be a leaving group, it would have to form a relatively stable base. All of these are carbon species, so they would make a really strong base. So there is nothing that's going to leave here. So this will just sit and wait until in the next step we add in that proton source. And so in the final step of the reaction, we're going to be adding in our aqueous acid, so H3O+, and we've got a base, right? We've got that alkoxide there, and this should grab a proton from your aqueous acid and form an alcohol. Okay, so we should be able to see how we've added the carbons from here. Let me go ahead and number that carbon chain for us. So 1, 2, 3, 4. So carbon 2 was the carbonyl carbon. That was what it was attacked. And so by numbering these, we can just make sure that we've still got them all in our product every step of the way through that mechanism. And then, of course, we can recognize that this is option C.